Welcome back, everyone, and hopefully you're coming from my composites overview video where we talked about a beam with composed of multiple materials and in which what the strain profile and the stress profile look like. And one thing you always know is that the strain profile is linear, regardless of the materials, as long as everything is bonded together. But the stress profile, because of the different moduli in the two materials, has some discontinuities involved. So right here, I have like the step going on, and that means I can't apply this flexure formula. And so here in this video, we're going to talk about a technique called the transformed area method that I've written down here, in which you can do to analyze a composite section. And the idea of the transformed area method literally is to transform one area into the other, maintaining force equilibrium so that you can analyze the section using this flexure formula. Okay, and so here I have really here the intent is I want to change here in this development or derivation, I guess. I'm going to take material one or area one, area of material one, okay, area of material one, and convert it into an equivalent area of material two based on force equilibrium. And one thing you should know, and that I'll show you again later, is that you can't change, whenever you change the cross-section area to transform, you can't change the height, because then you're altering the strain profile. And the one thing that stays consistent between the original composite section and the transform section is the strain profile, and that has to stay the same. And if you change the height of any of these areas, then the strain profile changes, and that becomes no longer feasible for you to analyze that way. And so here, if I have this transformed area, I'm going to take this material one, this top material that was purple above, I'm going to turn that into material 2. And so what's going to happen is I'm going to have a new dimension here, which I will call B2 right here. B2 right here. And the heights here are going to be the same. So here I'm going to say here. Oops. Don't crash on me. Thank you. Okay. Here H1, and this is H1 still, and this distance right here is still H2 down there. Call this H2. I don't know if you can see that. Hopefully you can see that. And here nothing's the same. I'm sorry, nothing has changed. And here the strain profile is it's identical to the one above here. The strain profile has not changed. Okay, the strain profile is the same right here. And what I want to do essentially with the transformed area method, let's see, where did I have the neutral axis? I had it up here somewhere. The neutral axis doesn't change either. That's another nice little thing to know. Here, my strain profile looks like this. Here's my strain profile. Here was that compressive strain, and here was that tensile strain. Or just two locations really, and I have going on right here the neutral axis, which I want to keep that in green so that we keep it color coordinated right here. And if I transform the area all into one material, then what happens is I really end up with a stress profile. I want to transform the area, so I get a stress profile that looks like this. Something that you've seen before, and which is where I have compression here, right here. This is not the same as that stress that was up here. This would be sigma prime, some new stress value, and then or equivalent stress value here, and then here this would be the tensile. Right? This would be the tensile, like that right here. And essentially what I want to do, and in this I want to do is transform this area into the equivalent material, so I can use the flexure formula, sigma equals minus my over I, on the transformed area, and then come up with a stress profile like this. And look at that. With this transformed area, I can use this equation, whereas I couldn't before. And this is how it would work. And the question is, because I can't change the height, what would have to be this new width of the transformed area, the area that I'm transforming, in order for me to maintain equilibrium. And when I say equilibrium here, this equilibrium right here is that the force resultant over here, and I'll call this the force resultant of this stress block or this volume right here, F1, I'll call that F1, has to be the same as the resultant of this stress block here, F prime. I'll call that F prime. And so here, now I'm going to go down over here. And so let's see if we can come up with the relationship between this B1 that is typically given to this transformed B2. All right. So here by force equilibrium. So here by force equilibrium. So these forces, really, it just means the forces have to be the same. Forces staying the same here. I would have F1 is equal to F prime. And the calculations for those is the stress block. So this is a linear trianguloid, I guess, right? Anyways, for F1, it would have been 1/2 sigma compression, the stress, and then times the area that it's acting on. So that's B1 times C, which is equal to 1/2 sigma prime, this new stress, times B2 times C. And this depth right here, because the neutral axis hasn't changed and the heights haven't changed, this C is still, this is still the distance C as it was before above. And you know, this cancels, this cancels, this cancels, this cancels. That's good. And now let me substitute Hooke's law into the stress values. And so I know that before I had E1 times the strain times B1 is equal to sigma prime in this case, because I've transformed this all into material 2 right here, is going to be E2 times epsilon times B2. And the strains, because my strain profile hasn't changed, oh, this is my strain and compression. Okay, this is the strain and compression, this value right here. Those strain values don't change. The strain profile has no change whatsoever. So it cancels here. And that tells me that B2 would be equal to E1 over E2 times B1. And if I want to transform this old B1 into B2, this new width B2 is equal to this old B1 times E1 over E2. Okay, and so here, this term right here is often called a modular ratio. And you know, if you're doing reinforced concrete or in a lot of textbooks, they use the symbol N, okay, for the modular ratio. All right. So hopefully that was the and once you have this new dimension right here, you've got you can use. So once you get this new area right here, you get this new area. So really in these composite section beam analysis for the section, the approach is really as follows. It's, you know, isolate your section, transform into one material using this relationship right here, E1 over E2 times B1 equal to B2. Then calculate geometric properties. Okay, you're going to need to find your centroid, Y bar. You're going to need to find your moment of inertia about the horizontal axis. Because once you transform it, then you can find what this distance is right here, like this distance right here. You can find this in the transformed section, and that won't change going back and forth. And then you can calculate your moment of inertia for this whole thing as well. Then, right here, then you'll calculate, I would say, draw this transformed stress profile and calculate values using sigma equals minus my over iz. And that's this right here. This is the transformed stress profile. Okay, right here. And once you have the transformed stress profile, you're gonna have all these numbers. You're gonna know what this number is. You're gonna know what that number is. Then you have a couple of options. One, you can go back and draw the strain profile. Okay, so here, this is kind of the sure way to do things is to draw the strain profile. And once you have the strain profile, you can go back up here. You'll know this right here. You'll have the strain profile. You go back to the original cross section, and then this every single point here, right here, will be multiplied by E1. Everything on this line right here. Let me do that in purple. Right here. Everything, every strain value here will be multiplied by E1, and you would get this part. And then every value, every strain value here would be multiplied by E2, and then you get the composite section, stress profile of the composite section. And some of you may be wondering, how do you get the strain profile? Well, if you've got this stress profile, you can just divide every single one of these stress values from that you've calculated from the flexure formula. You can just divide them by the modulus of elasticity E2. So really, this thing right here, you would back calculate sigma prime over E2 right here. And then this is equal to whatever that is. I'll just call that sigma, I don't know, sigma bottom right here. Sigma bottom, this is sigma bottom over E2. And then you just draw a line, bam, and you know where this point is, so you're good to go. And then you go back and calculate the stresses. So hopefully that cleared some things up. And I will do an example in the other video. All right, enjoy. Bye.